This presentation was delivered at the 2024 IEEE World Congress on Computational Intelligence. The authors are Derek Yadgaroff, Alessandro Sestini, Konrad Tolmar, Aisha Ushilakele, and Linus Gislin. Alessandro Sestini delivered the talk in Yokohama, Japan on July 5th, 2024.
Hi everyone, I am Alessandro Sestini. I am a research engineer at SEED, that is a research lab within Electronic Arts, EA, where we study how to apply machine learning for video game production. And in this talk, we're gonna see how to improve generalization of game agents with imitation learning and data augmentation. We will see why we need game agents, especially for game testing, and why and how data augmentation can help us in this task. This project was in collaboration with Uppsala University, and the main driver of this project was Derek Yadgaroff, that was a master's student intern at SEED, and I was his main supervisor. So let's start talking about why we need game agents. So games are increasing in size and complexity, and testing these games is becoming infeasible for human testers. That's the reason why recently game companies have started to use automated game testing solutions. And there are many ways to develop a automated game testing solution, and the mostly used nowadays is through scripting the behavior of the agent. So developers script the code of these testing agents and for designers that can test their games. However, this comes with many drawbacks, I would say. For example, in order to script and develop an agent that must test a complex video game, one needs the full understanding of all the underlying systems of the game. For these reasons, recently, many game companies and game studios have started to use reinforcement learning as automated game testing solution. And this solves some of the problem of scripting behaviors. However, still it has some drawbacks. For example, reinforcement learning is actually quite complex. It is one of the most complex branch of machine learning, and one needs a great machine learning knowledge to actually train an agent for testing a game. For these reasons, and in a paper that we published last year, we argue that imitation learning is the way to go. It's not perfect, it has some drawbacks, but it is the most suitable and it can be used by designers that do not know necessarily how to code or how to train machine learning models. But let's see an example why imitation learning can actually be good for game designers. Imagine you are a designer and you design this level, and now you want to test this level. Very simple trajectory, you want to open the door of this building pressing that button and go inside the building. And you create some demonstrations. With these demonstrations you want to train the blue guy over there, that is the agent that doesn't know what to do, so it acts randomly. But once you trained it, in just a couple of minutes, the agent will replicate what you did. But the real strength of this approach is that then you can modify the level and see how the agent would react and see how the level or humans would play this level. But there is a problem. So we said that imitation learning can actually help video game designers to test their game, but they need many demonstrations, especially for solving a common problem in imitation learning, that is what it is called distributional shift. So let's see an example. Imagine I want to train this agent with a very simple trajectory, shooting at that car and go to the goal position. I create only a bunch of demonstrations, and in a couple of minutes I can have this agent that shoots at the car. But if I move the car, then the agent doesn't know what to do. I need to create new demonstrations in order to train an agent that can actually generalize enough so that it can shoot at the car even if we move its positions. And so there is a simple solution to the distributional shift problem, that is creating new demonstrations. But of course, this is not ideal for game designers. We want agents trained with as less as demonstrations as possible. And how do other contexts in machine learning solve this problem? Well, with data augmentation. Let's take as example computer vision. In order to increase generalization of computer vision models, we create different versions of the images of the original dataset. For example, let's take this image as our original image in the dataset. We can now modify this image in order to create a variation of the original data sample so that we augment the original dataset with images that we know computer vision models are sensitive to. For example, rotating this image. And we can repeat this process with many modifications that we want, especially the ones that we know models are sensitive to. So the question is, can we do the same with agents and with imitation learning? Well, the answer is yes, but not in the same way. For many reasons, and one of these reasons is because we don't have images as our state space. So we have access to the game engines, so we can code perfect information to the agent. We don't need images. For this reason, our state space is composed of what we call vector observations, so vectors of real values, usually between -1 and 1, or categorical values, integers that represent some types of objects. And can we augment this dataset? Well, there is a paper called Surprisingly Simple Self-Supervision for Offline Reinforcement Learning that says that yes, you can actually augment this dataset if you find some meaningful modifications in order to augment your samples, your original samples. So, for these reasons, we tried to find meaningful operations, meaningful modifications in order to augment our dataset. And we found 6 modifications. Gaussian and uniform noise, where we augment the original state, adding some noise sampled either from a normal distribution or a uniform distribution. Scaling, where we multiply the original state with a value sampled from a uniform distribution. State mix-up, where we basically mix up the current state and the next state. And continuous dropout and semantic dropout, where we change to 0 some values either in the continuous part of the state space or in the semantic part, in the categorical part of the state space. And these are the modifications that we found that are actually meaningful in our use case. And the way we train the agent is actually pretty simple. So suppose that we have our dataset that can be augmented. The goal is to optimize the maximum entropy objective, meaning that we want to maximize the log probability of the policy given a state and action couple sampled from the demonstration dataset. And we collected our demonstrations in the environment that we saw at the beginning of this presentation, but since we want to test generalization, we actually test the agent in 4 different testing environments that are modifications of the original one, in order to simulate what a designer does when he changes the game or the layout of the level. And the way we augment the dataset is pretty simple. We create our first set of demonstrations so that we create our original dataset. Then we choose augmentations combinations, because we can combine augmentations together, and in this case we combine at most 3 augmentations together. Then we augment our original dataset, and we train and test the agent. The state space of the agent is composed of 3 main elements. The first one is some egocentric information of the agent, for example, the position, current health, or ammunitions. The second part is related to some entities information, basically the information relatives to objects of interest, important entities in the environment that the agents needs to know in order to solve the level, and a semantic map, a 3D matrix that represents the space around the agent. It's a 3D matrix where each value represents the type of object in that position, and since it is egocentric, it moves with the agent. And the neural network is pretty small, but not that trivial. But since it is not the focus of this talk, I will not focus on the details of the neural network, but we have published a previous paper that talks about the specific of this neural network. So, what are our research questions for this project? The first research question is, can we find at least one data augmentation combinations that can improve the results and the performance of the original agent, the baseline agent, the one that is trained with the original dataset without augmentations? Because in the end, we need only one combination that can improve the performance. The second research question is, what is the best combination of augmentation that has the highest performance on all the testing environments? Meaning, is there a combination that outperforms the baseline in all the testing environments? And the third one, what is the single most effective augmentation, if there is a single most effective augmentation? And let's answer the first question. So for the first question, as we said, we train many models combining different augmentations. In the left column, you can see all the augmentations together. And we train more than 200 models, but in this slide, you can see only a subset of the models that we trained and only a subset of the models that outperformed the baseline. And as you can see, there are many combinations that actually outperform the baseline. And yes, so augmentations can yield very large improvements over the baseline, sometimes almost doubling the performance of the baseline. However, if you see very well, there is a very large standard deviation. And this indicates that models may be sensitive to training parameters. We added a lot of hyperparameters, for example, the mean and standard deviation of the Gaussian distribution, or the parameters of the uniform distribution, and these models are sensitive to these training hyperparameters, so it can be complex to find the best performance using data augmentation. For the second question, consistency, if we can find a combinations of augmentations that can outperform the baseline in all the testing environments, well, yes, we have 6 combinations that actually outperform the baseline in the testing environments. Surprisingly, none of these 6 models is the highest performing model of the previous question, meaning that there is a trade-off between the best achievable generalization performance and consistency over all the testing environments. And for the third question, what is the single most effective augmentation? Well, our studies said that there isn't a single most effective augmentation. Yes, scaling is the one that gets the highest results, but it's closely followed by state mix-up, continuous dropout, and Gaussian noise. So there isn't really a single most effective augmentations, but rather is the combination of augmentations that outperform, that increase and improve the results. Surprisingly, however, uniform noise and semantic dropout do not seem to be really meaningful in this study. But let's see an example of an agent trained with augmentation in a relatively complex trajectory. The agent needs to interact with the environment with some objects, and we could train this agent with almost 5 minutes of demonstrations and 5 minutes of training with data augmentations. So in a very short time, we could actually train a good agent. And The same agent trained without augmentations, it can get lost in states that it never saw during training, and it can have some difficulties in recovering from these states, or it can get stuck in some local states contemplating the elevator forever. In conclusion, we saw that data augmentation can actually improve imitation learning agent, especially in generalization. But we also said that imitation learning can actually be really useful for video game development. This means that video game development can actually be improved by data augmentation. And due to the lack of time, I couldn't go through all the experiments and all the environments that we use for this project, but if you have any questions, you can reach out to me and I will be very pleased to answer all your questions. Thank you.
For more information, please visit our website at seed.ea.com.